Uh, Welcome everybody to the MuxLab webinar AV over IP review and an introduction to the product line. Bienvenue à le webinaire de MuxLab. My name is Jose Mozota. I'm going to be your presenter today. I'm a CTS, CTSI, HD-based authorized trainer, Dante certified, and SDVOE certified also. And my company is Fremen Solutions. I'm a training consultant, so I just focus on preparing and delivering training material for the customers. When you say we're going to talk about AV over IP and we only have like 1 hour, you really have to focus on what it is that you're going to be talking about. So our goal today is to review the importance of bandwidth as it relates to IP transport. If there is something that is critical to introducing any signal into a network, it's bandwidth. And as we all know, the bandwidth of our AV signals is extremely high. So how are we going to manage that? Then we're going to mention 1 or 2 concepts of IT that are relevant to that management and transport of the digital AV signals. And the idea is to provide you with some tools that will allow you to make a decision, because as we will see when we show the product line of MuxLab, it is quite extensive and there are many choices. So how are you going to choose what's the best solution for you? And we're going to review those solutions. And please participate. Please remember that there are no wrong questions. Many of you may have the same question and nobody asked the question because they think that it's a silly question or no, it doesn't make sense to ask that. Please ask the question and I will try to answer them in real time if appropriate. So the agenda is going to be, why do we want to do AV over IP very quickly? We're going to look into bandwidth for AV signals, IT concepts when it comes to networking. Then we're going to talk about compression, because we're going to come to the conclusion that we need to reduce the bandwidth, and compression is the way that we do it. And that's also the key component of the solutions that you can normally purchase. When you decide to use a solution, essentially, depending on the solution that you get, the compression is going to be fixed, but you can select which solution you're going to get. Also, the transfer protocols are going to be fixed, but you can also select which transfer protocols you're going to get. So the more you understand about the compression options and how they are different and the protocols and the way they transfer the signal, the better the solution that fits your needs you're going to select. And we're going to quickly talk about what I talk about, the AV over IP triangle, which is the basis of most of our decisions when we're implementing an AV over IP system. And finally, we're going to have an overview of the AV over IP solutions of MuxLab. Just as a reference point here, and there will be a PDF available of this presentation for your future reference. If you are going to work on AV over IP, you should be aware of these industry alliance and associations. Otherwise, you're not going to be aware of what's going on at the edge of the AV over IP technology. So SDVOE, AFNU for the AVV transfer protocol, aims trying to develop a common protocol for Pro AV and broadcast. AVIXA for the training that they deliver for AV and the shows that they carry. SEMTI, because even though it's broadcast, it's now getting more and more involved with Pro AV. Big C, because don't forget that layer 1, the cabling that we use to set up the network and do our installations is critical, and that's what Big C worries about. SRT, because if you are into streaming at all, you should be aware of the SRT protocol that is taking over right now that market. And finally, the Audio Engineering Society and their efforts to make all the audio protocols compatible one with another. So try to be aware of these industry alliance and associations. And I always like to start my AV over IP webinars with a little bit of controversy. I hear a lot of people saying, oh, AV is IT, IT it's AV. Well, I'm sorry, AV is not IT, AV it's AV, and IT is not AV, IT it's IT, and they have both coexisted. What TCP/IP is a transfer method. It is just a transfer method for an AV signal. When we work on AV, we have content that we want to deliver to the people that are going to consume that content. And in order to do so, we need to transport the content to the people. We traditionally done that with HDMI. We have done it with all kinds of cables. Well, TCP/IP is just a transport method. It is a very powerful transport method, but let's try not to understand it for what it's not. It is a transfer method for an AV signal. Now, why do we want to do AV over IP? Well, I mean, it is so flexible. It is so convenient. It allows you to do remote management instead of having to actually go somewhere to see what's going on with your boxes, your cables, your connections to the matrix switches. You can do it remotely. It's easy to install because networks are pretty well known and they are installed already. So all you got to do is have the necessary equipment to connect you to a switch and have the necessary equipment to connect you out of the switch into your display, speakers, whatever. It allows you to do video walls very easily. Nowadays, you can get very low latency solutions with even 4K 60 and digital signage. So there's so many things that make AV over IP interesting. And one that I like very much also is the architectural rearrangement can be virtual. So if I'm showing a content in a particular display and I want to change the display that I'm using to show the content, I don't need to go there. I don't need to connect and disconnect the cable. I can just sit in my control laptop or app and say, do it, and the network will understand me and will do it. So, but what do we need to know when we want to do AV over IP? AV over IP, we have networks around the world, and the networks have been there for quite a while, and they are transporting signals of all kinds, and they're allowing people to communicate all over. So we are the newcomers to this world. So what do we need to know? Well, number one, we need to know, how do I get my content into the network? Okay, I'm going to connect kind of equipment, a black box if you want, to the network, and that black box will put my content into the network. What does that mean? Once the content is inside the network, I should also try to understand, how does the content travel from one point to another? Because in case that there are any issues, that would allow me to troubleshoot, and also in order to determine what solution do I want to implement, it is very important to understand how that content travels. The other thing that we need to know is, how do we get a special treatment? You know, networks by definition are what it's called best effort. That means we'll do our best to carry your signal. And networks have always been the great equalizer. Networks couldn't care less if we put in there an AV signal, an email, a file transfer, an FTP, web browser request to see a web page. For the networks, all those are, at the end of the day, zeros and ones that are going around the cable on layer 1, from frames that are going around on layer 2, packets that are going around on layer 3, and segments that are being transported in layer 4. So finally, they reach the application and the user of the application. Fortunately, there are ways that we can get a special treatment, because that doesn't work for us on AV. Our signals cannot wait for the best effort. We cannot hold the movie until the network is ready to deliver it. We want to deliver the movie continuously and immediately to the person that wants to see the movie or listen to the music. So that's very important. Also, how do we get a special treatment? And finally, how do I get my content out to be shown, to be listened to be stored, etc.? And that's going to be very related to, how did I get my content in? So the way that I got it in is the way that's going to determine how am I going to get it out of there. So the issue that I'm going to focus today on the AV side is the bandwidth, because definitely what limits what you can do on a network is the availability of bandwidth on that network. Most networks that you're going to deal with are going to be 1 gigabit networks, so nothing bigger than 1 gigabit can go into the network. But the more the bandwidth of the signals they put in, the more that you can actually interfere with other things that are happening in the network if you're working on a converged network. And if you want to create your own network, that also has its own issues. So what limits everything is bandwidth. So let's make sure that we are on the same page when it comes to understanding the bandwidth of an AV signal. The first point is that AV signals in general, once they get to you for transport, they are already compressed. It's what would be called color compression. It's called chroma subsampling. That has been used forever to reduce the bandwidth, because when we produce a signal, and when we produce it, we do it in what is called 444, which means it has all the content of color and all the content of contrast. The luma and the chroma are all there. Producers from day one realized that once you do that, the bandwidth of those files is so high that it's very hard to manage them. So in order to do a Blu-ray, in order to do mobile television, in order to store them on a video cam, they found ways in which they could reduce the bandwidth of that signal by fooling the human eye, by fooling the human brain. They realized that they couldn't fool us when it comes to contrast. If you remove contrast, nobody likes the final image. So all the chroma subsampling methods have 4 on them, indicating the contrast has been kept constant. But they found out that you can get rid of a lot of color. You can get rid of half the color. You can get rid essentially of 75% of the color of an image. And you know what? The human eye essentially makes up for what is not there. So it is very smart, our brain, and that allows us to reduce strongly the bandwidth of a signal by doing chroma subsampling. This is something that we don't control essentially unless we work in production and broadcast. This is something that is given to us. Any Blu-ray player you have ever seen, it's at 420. Okay. Now, how do you calculate the bandwidth of a video signal? Well, you have to understand what is it that you're transmitting. So each image that you're transmitting will have a resolution, and that is going to be related to a lot of pixels that are the components of that image. So you start with that. If you have a 4K signal, UHD, you have 3840 by 2160. So if you multiply those two numbers, you get the total number of pixels you're transmitting. Afterwards, you have to ask yourself, well, how many frames per second am I transmitting that have those images? So typically we could say 24, 30, 60 frames per second. Let's choose 60 and put 60 on the equation. Afterwards, we have to realize that each one of those pixels needs color information. We have to provide 3 colors information, and also it has a certain number of bits that are actually used to define the precision with which you can see the colors, with which you can differentiate one red shade from another red shade. That's what's called color bit depth and number of graphic channels. Typically, bit depth, we used to use 8 for 1080p. Nowadays, we use 10, 12, or even 16. So let's say that we put 8 in here, which would be the lowest possible bit depth that we use for a video signal. And then for color, we have 3, either RGB or CY, CVCR, but it's always 3 graphic channels. So we multiply by 3. And at the end, we say, well, did we do chroma subsampling? If we didn't do chroma subsampling, then that's the bandwidth that's calculated. If we did chroma subsampling, we can multiply that by a number to make it smaller. But if we don't do chroma subsampling of a 4K UHD, 60 frames, 8-bit color 444, we end up with 12 gigabits per second. And as you can see, that will never fit on a 1 gigabit network. Actually, it will not fit on a 10 gigabit network, which is the second one that sometimes you can find on the enterprise, unless you're going to more specialized environments like a broadcast where they work with 25 gigabit networks. So there is no way that you can put that signal into your network. And I made a graph here that will be in your PDF that I think is very useful because this graph calculates the bandwidth of different combinations of signals, resolution, bit depth, frames per second, and it's done for a 420 signal, so that has been chroma subsample. If you want to know the value for a 444 signal, you simply multiply this number by 2. And as you can see, this is 1 gigabit, so nothing fits on a gigabit network without compressing. Even on a 10 gigabit, you are actually restricted to certain types of signals without compression. And just to remind people that other methods of transport are still alive and important, look at the bandwidth of HDMI 1.4 at around 8 gigabits, HDMI 2.0 at 18, HDMI 2.1 at 48. So if you do need to transport a signal that has a high bandwidth without any compression, then point-to-point may be the answer to your problems. And anybody in the audience that is an expert at HDMI bandwidth and starts wondering why the numbers that I'm giving here are lower than the numbers that they know for HDMI. Remember that HDMI adds 2 bits for the transition minimized differential signaling transport, and that increases bandwidth by 25%. So any signal here, when transported on an HDMI cable, it actually has an effective bandwidth that is 25% higher than what I'm showing on this graph. Now, what happens with audio? Well, with audio, not much happens because when we digitize audio, even using the Nyquist-Shannon theorem sampling method of at least twice the frequency, the highest frequency on the sample, even when we do a DVD audio at a sample rate of 192 kilohertz, which is much more than you need, you normally need 44, 48. If you go to 24 bits per sample, which is the maximum that most people are doing nowadays, even though there are already systems to do 32, 6 channels of audio 5.1, you only get to about 27 megabytes. So as you can see, the bandwidth has never been an issue for audio over IP. That is why historically, most of the AV over IP methods that were developed and were implemented for many years were only based on audio. Most of the solutions that we had were based on audio from the time of Ethernet, CobraNet to the introduction of Dante, etc. Everything was audio simply because we didn't have a problem with audio bandwidth, but we compress it mainly for storage considerations. When people started wanting to have 100 songs on an iPod or 300 or 1,000 songs on their iPhone, then we did compress the audio for storage considerations, but not because it's a bandwidth issue when we're trying to transport it. Okay, so in order to get our signal into the network, this is what we need to do. If the signal is analog, and audio essentially it's an analog signal, then we need to put it into a box that is going to turn it into a digital signal. So that's called pulse code modulation. Once we have the digital signal, that by the way with audio, it's a few zeros and ones, so megabit range, then we may need or not to compress it. If it's for transport, we don't need to compress it. But if we have a video signal on the other side that it's already digital, that has a lot of zeros and ones. I show you on the table that has gigabits of bandwidth. So we do need to compress it. And the idea is to reduce those zeros and ones to less zeros and ones and still have a good representation of the original signal. And what we're shooting for here, it's as low as 3 megabits per second, which is what you get normally television at home, between 3 and 6 megabits per second, to as high as 900 megabits per second, which you can fit into a 1 gigabit network if you're using certain types of compression, and that will give you the best possible reproduction if you're working at that level. We will discuss that you could go to a 10 gig network with other ideas, but that's more of a niche application. So let's talk about the more general application. And after that, the box that you have put into your system, this black box, the same way that your network interface card in your laptop, computer, node is just going now to encode all those zeros and ones in a way that the network understands it. So there are various types of encoding that doesn't pertain to us, Manchester encoding, non-return to zero, etc. But we're just going to put the zeros and the one in a way that they're going to be transported on the physical layer wire, and when they get to the network interface card at the other end, they're going to be understood by the switch, by the router, or by the black box that is going to decode this signal and make it available for consumption. Okay, so that was about the AV signal. Bandwidth is critical, is too high, we need to compress it. Now let's talk about one or two things that we need to remind ourselves of on IT when we're going to work on the network to carry a signal. There are two types of networks really that we work with. We work with the local area network, which is the one that happens in the place where we're living. It's all related to switching, but we sometimes go out of there into the world, the wide world web, the internet, or our own wide area network. If we are in a campus, could be a university, could be buildings, various buildings of a company that is running a campus. And those two networks, the LAN and the WAN, are completely different. The LAN that you actually build, run, operate, and create has very known capacity. It has very low packet loss. That means that the packages that are traveling through the network don't get lost, don't get damaged a lot. It's only very, very little. So most of the packages are coming through, and the latency is extremely low because only latency that you have in those systems is based on the transport, on the switching, and in some cases, if you're compressing on the line, on the compression or the establishment of certain protocols. But you have very, very little latency. Now, when you decide to go on the internet, when you start thinking about streaming, when you're thinking about collaborating between sites that are remote and you need to connect to the internet for that, you are going to run into all kinds of problems. The internet, you don't know the capacity of the internet. You don't know if the route that your signal is going to take, it's congested or is not. You don't know if it's going to find routers that have a capability of bandwidth lower than other routers that you could use. So you don't know what's going on there. You just hope that things are going to happen. There is a lot of packet loss. So most of the signals that are sent through the internet suffer from packet loss, and that could at some point impact your ability to send an AV signal. It also has jitter, in which the distance between the packages gets randomly increased. And TCP/IP actually works to recover those things. So there are ways in which you can recover from all those events, but that causes high latency. So you are in control on the LAN. You're not allowed in control on the WAN. However, the suppliers of solutions that can actually work on the WAN have come up with all kinds of ideas to allow you to work with this high latency. As you know, for example, when you're streaming a movie on Netflix, that movie is going to be buffered before it's sent to you. So that through that buffering, you can try to play it in a way that is going to be agreeable to the person that it's actually watching it. The other thing is, if you decide to go AV over IP, there's something that you should know, and that is what are the minimum characteristics of switches that you would use for AV. The first one is you want to have a full layer 2 and layer 3 managed switches. So as you know, layer 2 is the switching layer, is the network layer. Layer 3 is the data layer. Layer 3 is the network layer, is the routing layer. Now, why do you want full layer 2 and 3 if you're going to stay, for example, in your local area networks? Because you are probably going to use virtual local area networks in your AV system. You're going to want to separate your audio from your video, from your control, from your lighting. And in some cases, you're also going to have a control network that can control all those different networks. Well, in order for VLANs to communicate with one another, you need a router. Because when VLANs are established, the members of the VLAN cannot communicate with one another without a router. And by having a layer 3 switch, then the switch has the routing capability built in and makes it easier for you to actually be able to set up and manage VLANs on an AV over IP system. The second thing that you want is the switch will be a little bit more expensive, but you want your switch fully non-blocking. Fully non-blocking means that all the ports can work at the same time at full bandwidth. So if I have a 1 gigabit switch, 48 ports, and I connect 24 transmitters, sending each one of them 900 megabit signals with JPEG 2000, all the 24 signals can go through because the switch is fully non-blocking. If the switch is not fully non-blocking, the specifications will tell you the maximum amount of signals that can go into the switch fabric before the switch says, you know what, that's too much for me, I cannot handle it, just get in line and wait. Okay, so very important to use fully non-blocking switches. The next thing is you need to buy switches that can run IGMP version 2 snooping and BIGMP queries. Why? Because most likely on AV over IP, you will want to do multicast. That's the most difficult thing to do. Most people don't realize that doing multicast is not easy the moment you go beyond one switch, but nevertheless, even for one switch, you need to run IGMP. Otherwise, you're not going to get multicast, you're going to get broadcast. So your switches should be capable of running IGMP. The next thing is please avoid green switches. I know that we want to protect the planet. I know that we want to get green in all our applications, but green switches that go to sleep when they are not being used are really bad for audio transport, because when you want to use the port, it takes a certain amount of time for the port to wake up and become viable. And the problem for that is then that your audio signal is going to be out of sync. So avoid green switches, have switches that the ports are operating all the time. And just be mindful and make a friend on the IT department at the companies you're working with or in your own company, because the moment you deploy more than one switch in any kind of application, multicasting or not, the moment you have more than one switch because you need more ports, because that's the physical topology that you have set up for your network, you're going to need to stack or uplink the switches, and those calculations can be tricky, especially if you're going to be using AV signals that have a relatively high bandwidth. Remember, IT people are not used to having issues with high bandwidth signals traveling their network. Every time that we're sending these packages of the web browser or an email, etc., the amount of information that is being sent is nothing compared with our AV signals. So even they have issues sometimes understanding that, and you need to have a conversation so that they understand why you may have a problem and help you calculate the uplink of the switches correctly. Nowadays, a lot of manufacturers will also give you support on that when you purchase their switches. Okay, so we have the signal that is being compressed, we have the network, and we have the right switches to put actually into that network so that we can operate. There are many protocols that are used to transport AV signals. Like I said previously, most of them will be selected by the manufacturer of the boxes and will not have a lot of impact on what you do. However, when you work on broadcast, there's a protocol that has been developed called SMPTE 2110 that is now available also for people that don't work in broadcast, and it gives you capability of designing new workflows. And I just want to explain to you what 2110 is, because we do have a line of products that allow you to use 2110 with an HDMI signal. So in broadcast, your signals have audio, they have video, they have ancillary data. It can be subtitles, it can be ads, it can be anything you want that it's ancillary to the audio and the video. And they also have very precise timing. And for a long time, they use SDI connections, 3 gig times 4, 12 gig SDI connections to transport that signal in the broadcast studios. However, they're always looking at ways to improve the workflows and the things that they do in broadcast. So they came up with a way to put that into AV over IP. So they developed SMPTE 2022, a protocol to just take the 4 signals together and put them into a network. But then they started to think, well, what if I want to work only with the audio or only with the video? So they developed SMPTE 2110 that allows you to break the signal into what is called the 4 essences. So SMPTE 2110 carries 4 essence signals, which is audio, video, ancillary, and time. So if I put a signal into a 2110 system, the signal will be broken into these 4 components. And as you can imagine, if I want to work with the audio, I don't need to de-embed the audio anymore. I can work with the audio. If I need to work with the video, I can work with the video. If I want to modify the ancillary signals, I can modify the ancillary signals. So that gives you a certain level of control over your flows that has resulted in people adopting new workflows in production and broadcast, but it is also something that Pro AV is looking at, because if you can get a box that will actually break your signals into these 4 signals, then once they are inside the network, you can play with them, you can massage them, you can program them, you can rejoin them in some kind of production device, and that gives you a lot of possibilities when you want to think about potential for changing the way you work. And the AV over IP triangle that I mentioned is something that you're going to be dealing with every time you want to do AV over IP. and that is the relationship between bandwidth, video quality, and latency, and in the middle, the mighty dollar. So if you reduce the bandwidth of a signal not very much, the latency will be not very big because the time it takes for the algorithm to do its processing will not be very long, and the quality of the video will be fairly close to the original. Let's say very good quality of the video. But that's going to cost you money, because if you don't reduce the bandwidth of the signal very much, you may need more bandwidth on your network, and that has an impact. On the other hand, if you reduce the bandwidth of your signal a lot, then you have more latency because it takes time to do that reduction. And the quality of the video will not be as good as the quality of the video of a signal that has not been reduced so much in bandwidth. It will still be good because, let's be real, you like your TV image and it's running at 3 megabits. So when people talk about video quality, let's be clear about what is the application, because in many applications, video quality is not that critical. You know that in sports bar, typically they run at 720p monitors. I mean, everybody's drinking beer from a distance, having fun, etc. So there are many things that come into play when you're talking about video quality. Even a very heavy compressed signal with H.264 will give you a video quality that will be acceptable for most users. But if I have a huge video wall in the entry of my corporate building, I wouldn't want to put that kind of signal in there. I would like something that better reflects the message that I want to send on a corporate way on that video wall. If they are doing an MRI of my head because I may have a lesion there, I want the video quality to be very, very high so that the doctors can actually look at what's going on in detail. So it is all about the application. Okay. So you're faced with a lot of choices. You have here a gigabit network, so you have set up your network and runs gigabit. If you're running gigabit network, then you need to bring all the signals below 1 gig in terms of compression. And for that, you will use compressions like H.264, H.265, or even the relatively older MJPEG that it's still relatively cheap and works very well. Or you will get JPEG 2000, which is a step up. It's a visually lossless compression. It will typically work between 400, 800 megabits. So it gives you a higher bandwidth stream, but again, less latency and more picture quality versus H.264, H.265 that are meant to reduce the bandwidth almost down to nothing. Now, if you have more money, and or if your application requires it, then you can set up a 10 gigabit network. You can use any of these signals on a 10 gigabit network, but that's not the purpose of doing a 10 gigabit network. The purpose is to be able to use something like Blue River NT compression, which is the one promoted by SDVoE, in which the signal is brought down just at 9 gigabits, enough to put it into the 10 gigabit network, but that gives you extremely low latency and essentially a picture quality that is totally undistinguishable from the original. Now, you may be in this audience somebody that works with broadcast. So if you work with broadcast, you either have 10 gig networks for some compressed signals, but you also have a 25 gigabit network that works with uncompressed signals. If you remember the chart that I show you, having a 25 gigabit network will allow you to transport most of the signals even at 444. And a 25 gigabit network will definitely be running on fiber. You cannot run it on copper. So that adds another level of cost, another level of complexity to the network that you're going to be running. And then you have people that want to access the content on a phone, on an iPad, or a tablet, on a desktop, on a screen, on speakers, in many, many different ways. And you may have signals that are high definition, 4K, 8K. So what do I do? Okay. How do I select a solution? What are my options in terms of implementing a solution that will fulfill my requirements? Well, From that point of view, we can come to MuxLab and see the possibilities that are being brought to us, because we do have a large AV over IP, let's say, product choice that can work in any of the verticals that you're normally dealing with. So if you're an installer, it can even go from the home theater to a boardroom system, or to medical imaging, or sports bar, or classroom digital signage. Actually, at the end of the day, an AV over IP system is something that is relatively simple, and it gets complex when you scale it up, but it's just adding hardware and adding hardware and adding hardware. That's what makes it different. So from the sports bar to the casino, the only difference is more sources, more displays, more distance between them. Or with an airport, same story. More sources, more displays, more distance between them. One point that we want to make from the beginning on AV over IP is that our solutions have been tested with Netgear and Cisco, so they are compatible with the most widely used switches on the IT world for LAN and WAN transport. And they also work with third-party drivers and plugins from suppliers like QSys, Crestron, etc. So that if you have those kind of systems, then you can always have our products interface with them. So how does a typical AV over IP arrangement looks like? And this is the one that I think you can look at and say, okay, I'm going to scale it up to whatever I need. The rules are very simple. You have sources, and for every source, you need a transmitter. Every source needs to go into a transmitter. This transmitter would be that black box that we showed at the beginning. So this transmitter will do two things essentially, or maybe three. It will actually compress the signal. It also, most of them have the ability to encrypt the signal. So if you want secure transmission, you have AES 128 encryption. And then they will have the network interface card at the RJ45 connection that will encode the signal to put it into the network. But you need one transmitter per source. Why? Because in the world of AV over IP, once the signal is inside the network, that signal can be reproduced as many times as we want, even though we started with only one signal. So this is not point to point, that if I need 4 of the same, I need 4 times the signals. Here, one signal goes into the network, and then the magic of multicast happens, and I can send it to 2 screens, 4 screens, 20 screens, 100 screens. It may be more complex, the programming, it may be more complex, the linking of the switches, but I can do it. So one transmitter per source. Then the signal goes into the network. Once it's on the network, we do have a digital network controller that you plug into the network, and that will allow you to automatically discover all the devices, transmitters, receivers, etc., and will allow you to establish your, let's say, your virtual architectural arrangement. So you want this source to that display, you want this sound to that speaker, etc. And typically you will also set up a router, wireless, so that you can make the signals available to mobile devices and to Mux Control, which is an app that will allow you to run the control on the network from a mobile device like an iPad or a tablet or a phone. On the other side, once the signal has traveled through the network, then once we take it out, the boxes do the opposite than the first box did. So the boxes will actually turn that signal back into an HDMI signal or a DisplayPort signal or into analog audio if we're going to put it into a speaker, etc. So it will do the inverse. Now, one thing please keep in mind, whatever was discarded by the compression algorithm is gone. So I don't like using the word decompress the signal, because decompress is almost like, I take something and I push it and I push it and I push it until I compress it. And afterwards I release the pushing and then it decompresses to the original. That's not the case with the algorithms that are used to compress AV signals. The algorithms that are used to compress AV signals throw away stuff. That's how they get rid of bandwidth. They throw away things that they decide you're not going to notice, you're not going to care, it's not going to make a difference to you, and they do it very well. But what is thrown away is lost. So when you go to your receiver box, you're essentially just converting all those zeros and ones that are coming from the network into a signal that you created here through compression and that you are now going to show on a display, or you're going to present on a speaker, or whatever way you're going to be looking at that signal. That should be very clear. People talk about compression, decompression, and that is not an accurate term. What you lost on compression is not recovered when you regenerate the signal. So when it comes then to what do I choose, typically we present the solutions that we have in this way because it makes it easy for you to look at them. So if you're looking at 1080p, we can work with Motion JPEG, which would be the most inexpensive way that you can actually compress signals to do HDMI extension or video walls. We can also add always, in all the solutions, we'll be able to transport infrared signals control, RS-232 signals control, PoE in many cases also, because nowadays most appliances will actually work with PoE, saving you from having to have all those transformers in the rack. If you move now to a 4K entry level, then or regular video walls and transport, then you can go with either a H.264, which is heavily compressed, or with JPEG 2000. And as you can see, the size of the stream varies. Here on the average we show 16 megabit, here we show 500 megabits, so it's completely different bandwidth that we're dealing with. However, the latency will also be different. Here it's only one frame, here it's 200 milliseconds. In order to compress more, it takes more time. And if you actually want to work with 4K 60 uncompressed, then we can go with the SDVoE Blue River NT solutions, and that will give you essentially what they refer to as zero latency, because it's less than one frame, but the signal is barely under 10 gigabits per second. And that is closer to what is called a lossless compression, where you don't really lose anything that makes a lot of sense. And if you want wall plates to connect your system, you can get that too. We have a product that I'm going to mention, the newer version, to do KVM, keyboard video monitor control, which is very useful in many applications to remotely control servers. If you want to do only audio, we can work with that. But then we also have here some interesting ST2110 solutions, where we can take a SDI connection up to 3 SDI, 9 gig without compression, or we can take a larger signal with HDMI and then go uncompressed on a 10 gigabit network. So that kind of shows you in two charts the different options, and obviously the people that you deal with at MuxLab can provide you more information about any of these particular solutions. Now that looks kind of confusing, so one thing we're going to throw you here, it's a sneak peek of our new branding that hasn't been published yet. It's going to be released at ISE. But what we're doing is we're trying to group the solutions in ways that will make it easier for the customers to decide what they want. So if somebody wants to do a low latency 1 gig, it will be a family of products, the MIP 100 that will do that. If you want to do low latency 1 gig 4K, it's another family. If you want to work with H.264, H.265 heavy compression, another family. If you want an SDVoE solution for your particular application that requires you, another family. And finally, if you want to work with SEMT2110, that will be another family. So hopefully, by grouping the products, not only on the way I show you on the table, but by families, you can go to the particular kind of solution that you're looking for, and that will help you make a better choice. Let's look at some applications here of some of those boxes that we show on this slide of products available. So this is the latest addition to the KVM HDMI or IP PoE extender. So this one can do up to 4K 60 and uses JPEG 2000 compression. So typically you're going to get around 400 to 800 megabit out of it. And as you can see here, the idea is to connect the server, for example, to the transmitter. It goes into the network. But then on the receiver side, even though it's a receiver, networks are duplex, full duplex. So that means that the signals can go in both directions. So in this case, we do have the monitor, for example, but we have a keyboard and we have a mouse. And by connecting that to the USB port on the receiver, we also make those signals available to the server on the other side, going on the other direction. So full duplex means I can go this way, I can go that way, I can communicate in one way or the other. And that makes it a very, very powerful solution for controlling a server, for controlling a host laptop, whatever you want to do, controlling from a keyboard, a mouse, or actually having it on video by using this KVM controller. And as you can see here, we also have the MuxLab network controller on the network. We like using an appliance for that. Some manufacturers will use software's products for that. We believe the appliance is a more powerful equipment that we can use. It's a Linux-based appliance. Sorry. Now, if you want to use the 2110 capabilities that we explained before, sorry, of being able to use the different streams that you can get out of a 2110 application, then we do have a solution where you can connect your HDMI products, cameras, monitors, etc., whatever you want, to the box, and the box will create the streams for 2110. So inside this network, you will have one stream for audio identified, one stream for video, one stream for ancillary, one stream for timing. And then you could actually go in and add equipment to this network that allows you to interact with each one of those streams separately. Okay, and in this case, we are also showing two 10 gigabit LAN connections because we use Class D redundancy. That means that we allow to set up two networks essentially on parallel, so that if one of the network path fails, the other network path will come in and take over. And we also implemented NMOS, which is Networked Operating System, for discovery and control of the connections, which is another one of the standards that AIMS is trying to introduce now in the market. And we also release now a similar product using SDI. So we can use 3 gig SDI for this connection. And obviously that means that we will send that particular stream uncompressed, but being 3 gig, it will be on a 10 gigabit network, and we allow that 10 gigabit network to be either fiber, or copper. And it's a very similar setup than the previous one. Now just we have a 10 gigabit network here switch, and we also have one connection per transmitter and one connection per receiver. And the controller, like we said before, will allow you to control everything that is happening. It will allow you to discover equipment, transmitter, receivers. It will allow you to set up a virtual, let's say, configuration of which signals are going where. And you can also download on the App Store or Google Play the Mux Control app, and that will allow you also to wirelessly, remotely control the system that you have set up for AV over IP. So the final question is, okay, you want to do AV over IP, how are you going to implement it? And I hope that with these tidbits of information that we gave you today, you see that the idea is to educate yourself. The more you know about what you're going to do, what the capabilities of the transmitters are, what the transport protocols that are being utilized are, and how reliably they will take the signal to the other side for the consumer to access that signal. That's going to help you make the decision. Also, we hope that by learning about the basics, you cut through the noise. There's a lot of noise in the industry. There's a lot of marketing noise, things that are not necessarily clear. And the more you understand the concepts, the more you understand the technology, then the better you can cut through that noise. And at the end of the day, what does the user need? Because this is all about the application. And remember, for anything that you do on AV over IP, you really have to join AV and IT professionals. You may be able to do it yourself if you're just doing like a dentist shop or something with one switch and 20 ports or connections. But the moment you start going into more than one switch, the moment you start going longer distances, the moment you want to implement 10 gig networks, then, and especially if you want to do multicast, you should have some IT support in your own company or in your support group or in the customer, so that you can talk over with them, because you will need help from IT to do a more complex AV over IP system. Thank you for having been here. I understand that there's always a draw for a card, and you will be notified who wins the famous gift card for having taken the time to share this with us. And if there are some questions, my contact information, it's on the screen. It will be on the PDF also, so you can reach me at my email, at my phone. I'm based in Ottawa. And you also have the contest information for the sales team at MuxLab, and the phone number, and anything that you need related to the commercial side of MuxLab, please contact them.